so I could not make. Oops. And yeah, and I also apologize because I'm not able to follow all the very interesting and nice talks at this conference. And I'm going to talk about entropic regularization of optimal transport, but for multi-marginal problems. So basically, I will describe in an easy and self-contained way, hopefully, two results. One, which is about the well-posedness of the so-called Schrödinger system, so the system of optimality conditions for the dual in the multi-marginal setting. It's a joint work with Maxime Laborde. And the second result I will describe is a linear convergence result for Sinkhorn in this multi-marginal setting. Okay, so please interrupt me at any time if anything is unclear or if the sound is bad or anything. Okay, so I will start. The first part will be kind of useless for most of you because you're all familiar with optimal transport, multi-marginal, maybe not, but entropic transport. So the first part of my talk will be devoted to a description of the problem I'm going to be interested in. Then I will give a proof of why this multi-marginal Schrödinger system is well posed in the standard sense of Adama, let's say, meaning existence and uniqueness and smooth dependence with respect to the data of the problem. And then I will say a few words about why the multi-marginal Sinkhorn converges linearly in a quite general setting, provided the cost is bounded. Okay. So let's start with Monch-Kotorovich, which you all know. So just basically to set up some notations. So you got a source measure mu, a target measure nu, probably on different spaces, a cost function C, and you look for an optimal plan, so a transport plan gamma between mu and nu, which minimizes the average transportation cost, so the integral of CD gamma. Okay. And of course, a key, and there are very good textbooks now about the problem. It's very huge effort since at least 30 years to understand this problem. I mentioned the books by Villani and a more recent one by Filippo Sant'Ambrogio. And of course, the cornerstone of the theory, a useful tool is duality. So the Kantorovich duality formula tells us that the dual, this is linear programming, so it comes also in dual form, as looking for potentials phi and psi, which maximize the sum of the average of phi against the mu plus the average of psi against the nu, with a restriction that the direct sum of phi and psi is less than the transport cost. Okay, so if given a phi, you look for the optimal psi, which is the largest one, you end up with the standard C transform notion. So given phi, the largest psi which is admissible is a C transform of phi. And as Gabriel mentioned, in fact, you cannot just take, if you iterate C transforms in the standard optimal transport, when you do 3 times the C transform to improve the cost, let's say, you get back to the first C transform. So the CCC transform is the same as the C transform. So if you do alternate optimization on this dual formulation, it will not drive you too far, right? But still, we know a lot about this duality because by complementary slackness, we know that optimal plans are concentrated where on the set of pairs X and Y for which the constraint is slack, meaning that phi of X plus phi C of Y should be equal to C of XY on the support of gamma. And for instance, in the quadratic cost, this leads to Brunier's theorem and to the fact that optimal gammas should be supported, should have a support which is included in the graph of the subdifferential of a convex function, okay, which links this problem to Monge-Ampère equation, for instance. Now comes entropic regularization. So you can view it as a trick or as an approximation, but it's in fact more involved than this, where you add a strictly convex term with a small epsilon in front of it, which is just the relative entropy of the cost with respect to a reference measure, which I will take to be the product of the marginals. Okay. So it's the same. You can, of course, absorb the transport cost, the integral of C d gamma in the relative entropy. And this regularization, this entropic regularization, is the same as minimizing the relative entropy of gamma with respect to the measure, which has density e to the minus c over epsilon, mu tensor nu, okay, among transport plans between mu and u. So pi of mu and u is a set of transport plans between mu and u. So again, this is a strictly convex problem, and at least formally, the structure of solution is easy to understand. You can write Lagrange multipliers for the marginal constraints, and at least formally, you can guess that the optimal plan gamma epsilon, depends on epsilon, should be of a product forms times the Gibbs kernel e to the minus c over epsilons mu tensor nu. But now the condition, and of course you can write this in exponential form. So if you define the kernel k as being e to the minus c over epsilon, you change variables a and b, the Lagrange multipliers, so you write them in exponential form as well. Now solving this the optimal entropic optimal transport amounts to find potential so that this plan has marginals mu and u. Okay, so this becomes just a set of two equations. You can forget that it comes from optimization. You look for potentials a and b in such a way that these two integral equations, so that one is equal to a of x, the integral of k b against d nu, and a similar equation between b and a. So it's a slightly nonlinear set of equations in terms of a and b. If you solve this set of equations, these two equations, then you have solved the entropic OT problem. So in exponential form, solving this problem is the same as saying that phi can be expressed as a function of psi by this formula. This is a sort of this is what we saw in Gabriel's talk, and this is a sort of soft C transform. It's approximating C transforms by log Laplace, if you want. So phi should be a function of psi given by the first formula, and psi should solve a similar equation. Okay, and these two equations, it's not very difficult to see that it's the Euler-Lagrange system for the dual of entropic OT problem, which amounts to find two potential which minimize the same guy as we saw in the convergence problem, so the integral of phi d mu plus the integral of psi d nu. But now you pay an exponential price by on the constraints we had before. Phi plus psi is less than the cost. You don't have this constraint, but you pay epsilon times the integral of this exponential against the reference measure, which is the product measure. Okay. So just a remark, a very basic remark, is that as in convergence problem, you have an invariance, an obvious invariance in the problem. If you add a constant to phi and you subtract it to psi, you don't change anything in this dual problem. And in the Schrödinger system, I will call the Schrödinger system this set of two equations. Phi equals minus epsilon log blah, 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 and psi equals minus epsilon log blah, blah, blah. And in terms of A and B, it means that there is a sort of multiplicative invariance. If you multiply A by a positive constant and you divide B by the same constant, you still get the system is invariant by this. So it means some normalization has to be made if you want to have uniqueness results, for instance. Okay. So of course, Gabriel described the Sinkhorn algorithm. Once you see these two equations, it's very tempting to iterate over the set of two equations to express A as a function of B and B as a function of A. And this is basically what the Sinkhorn algorithm does, which is quite simple. It's two lines of iterating. You look for a fixed point of the map if you want, and you do iterations of this map. And as Gabriel mentioned, there is a very nice approach to prove convergence, which is based on the so-called Hilbert projective metric. Projective means somehow that you keep track of the invariance by multiplying A by a constant and dividing B by the same constant. which is based on the theorem of Birkhoff, which shows basically linear convergence of visitor rates to a solution of the Schrödinger system. Okay. I mentioned that this proof does not work, as far as I know, in the multi-marginal case, because if you look at the Lipschitz constant for the Hilbert metric, there's a number of marginals -1, which shows up in the Lipschitz constant. So you cannot see it's a contraction as far as there are more than 3 marginals or more. Okay. And as was mentioned by Gabriel as well in the previous talk, you can see also Sinkhorn in terms of the potential psi and phi to do this sort of call transform. Instead of looking at A and B, you look at phi and psi. It's the same as block minimization or alternate maximization for the dual problem. So given psi, given phi, when you look for the best psi in the dual problem, you exactly have this formula, right? So Sinkhorn is the same as alternate maximization for the dual. So of course, there's let me mention a little bit of literature. It's related to lots and lots of works in different communities, in different settings. Something different communities call the same objects under different names. And of course, this audience is super familiar with the Schrödinger system, Schrödinger bridges, and related problems. First of all, the system appeared in the seminal work of Schrödinger in the 30s. Very early on, it raised the interest of great mathematicians, such as Bernstein in the 30s, later on Arno Berling in the 60s. Of course, I will stick to the static formulation, but there's a dynamic formulation for the quadratic cost, for instance, which has a flavor of large deviations. I should mention a very nice paper by Dawson and Gartner, the lecture note by Hans Vollmer, the work of Christian Leonard, which was instrumental to bring this problem to the optimal transport community. It's also very much related to stochastic control, and the work of Professor Mikami was very important in this respect. The problem of Schrödinger bridges has been extended in many directions, and many of people in Lisbon and their collaborators have been involved in very interesting developments in the unbalanced case. For instance, let me mention the work of Barada, of Lavenant, general metric spaces, the work of Léonard Mont-Saint-Jean, Tamanini, Vorotnikov, and others, the work of Conforti, Gentil. So it's a very active field of research. Related also to problem which has a flavor of incompressible fluid dynamics, the so-called Schrödinger problem, which Arnaud Don, Cruzero, Leonard Zambrini, building upon previous work of Huazue or Barada and Mont-Saint-Jean worked on. It's also related, some mean-field games can also be cast in these frameworks, something we used a few years ago at Mocaplan with Jean-David, Simone Di Marino, and Luca Nena. Solving the Schrödinger problem in the discrete case is linked to the so-called DAD problem, which in the continuous case has been very much studied by John Borwein, Adrian Lewis, Roger Nussbaum in the 90s. The algorithm comes also under different names in statistics. IPFP, the iterated proportional figure, iterated proportional fitting procedure, with works of Cesar, Ruchendorf, and others. And of course, in the last decade, it's been very much used for approximating numerically optimal transport, as was pushed forward in the seminal paper by Couturier. There's also an important paper by Galichon and Salanier, Couturier and Perez book, and Alfred Galichon's book on application of optimal transport to economics played a great role to make these methods popular. So now, okay, this is basically, sorry for it's a very long introduction, and I guess most of you are familiar with that. Now let me go to multi-marginals. So multi-marginals, now you don't have only 2 marginals to fit so as to make an average cost minimal. you got several spaces, x1 up to xn, a cost which depends on the position of all the particles. You got marginals mu1 up to mu1 on the different spaces, and you want an optimal plan, but a multi-plan, gamma, which has marginals mu1 up to mu(n), which makes this overall guy minimal. Okay, so I will not describe applications in details, but it comes in different settings. In physics, in particular, for instance, in studying incompressible fluid dynamics in the spirit of the seminal work of Brenier, for instance. Also, in so-called density functional theory in quantum chemistry, the cost is a Coulomb cost. It's a repulsive cost between the position of n electrons, and you end up with similar problems. There are problems in economics and in machine learning also, where you're also interested in multi-marginals. Okay, so we can mimic to the multi-marginal case what we saw in the two-marginal case. Let me mention also that there are much less general results available in the literature in the multi-marginal case. For instance, there are no general results which say that the optimizers should be of Monge types or things like this. They are very scarce in the literature, with a few exceptions, like the work of Brendan Pass. So it's very tempting, at least numerically, for instance, to approximate the problem by entropic approximation. So we can guess that the good approximation of the previous multi-marginal OT is to, you look at the product measure, you multiply by the Gibbs kernel, and you try to make the relative entropy between the transport plan and this guy as small as possible. You minimize this, okay? So again, formally, you can guess that the optimal plan should have a special structure. It should be the Gibbs kernel times the product times the product measure. And now the constraint is that this guy has marginals mu I, for which if you write it's the gamma epsilon in exponential form, as I did here, you just have to look for potential phi I, which solve this system 7, which I will call the multi-marginal Schrödinger system. So you look for potential phi I such that the marginal of this gamma epsilon, you take this ansatz, and they have the good marginals. This is system 7, okay? And the rest of my talk will be devoted to study this system, okay? So again, you can forget from now on, there is a big warning here. Of course, there are lots of things, and many of you, or many of your co-authors have been involved in the very important issue of what happens if epsilon. By the way, can you all hear me? Because I don't see the chat, so. Leonard?
Yeah, we can hear you.
Leonard, you can all hear me?
Yeah. It's okay.
Okay, thanks.
Thank you.
Okay, great, thanks. Okay. So I said there is a huge stream of research, which is still very active now, on understanding precisely what happens as epsilon goes to 0, in which sense you approximate the optimal transport problem, with similar contribution by Christian, and more recently by Giovanni, Soumik Pal, Marcel Nutz, Luca Tamanin, and many others. But for the rest of the talk, I'll do two things. I will not be interested in letting epsilon go to 0. I will stick to the system. So I will take epsilon to be 1. Okay. So for those of you who are not interested in the fixed epsilon case, you can just take a nap or go for a coffee or early lunch. And also I'll stick on the algebra, on the system. I will mainly forget that it comes from optimization. Okay, so the first question is this system well posed? So you give yourself mu i's, you give yourself a cost C, and you want to solve this system. Is there existence, uniqueness? Does the solution depend smoothly on the data? And this is what I want to discuss now. It's something we did a few years ago with Maxime in a quite general framework. So for the spaces, I will assume just probability spaces xi, fi, mi. So X will be the product, M will be the product measure, and F will be the product sigma algebra. Also, let me introduce, so the MIs will be reference measures, and I will look at marginals mu I, which are density with respect to these reference measures. And to use notation, it will be convenient to use the notation minus I to denote all variables except I. Okay, so now I will write M minus I, which will be the product measure of all the nj with j different from I, and so on and so forth. Okay, so the problem is the following, and okay, I will work in an L infinity framework. So note that I will not assume any sort of continuity, or I will not even assume that the xi are Polish spaces, but I will assume that the cos C is L infinity on the product space. Okay, this would be mainly my, it's a limitation, but it's quite an abstract assumption. Okay, so I will denote by L infinity of X of the individual space Xi and of the product space X. And when I put a plus plus, it will be the interior of the non-negative cone. Okay, the function which are bounded and essentially bounded away from zero, M almost everywhere. So I give myself the kernel K, which is exponential minus C. So it is in the interior of the positive cone of L infinity. I give myself also strictly positive densities with an obvious compatibility condition that the integral of mu I dmi should not depend on I, otherwise I have no chance to find a plan which has the mu I mi as marginals. And I'm looking for potentials phi I, which are also bounded, such that for every I and mi or almost every xi, I add this equation. So mu I of xi is the exponential of phi I xi times this integral. Okay, this is the same system as we had before in this business. So this is the multi-marginal Schrödinger system, right? So of course, as I said, for the two marginal case, there's an obvious compatibility condition on the mu I, let's say the data, the marginal mu I, which is this equation 9. And there's also an invariance of the Schrödinger system itself, the system 10 I want to solve, meaning this, if I add a constant lambda I to the phi I and the lambda I sum to 0, I change nothing to the problem. So there's an obvious invariance, so I can add a normalization to the phi I, okay, which is what I'm doing in this slide. There's no loss of generality in adding normalization constraints, which are the n-1 linear equation, that the mean of the phi I should be 0 for the n-1 first margins. Okay, this changes nothing, but imposing this constraint, at least I have a chance to have a unique solution. Okay. Again, I can notice that the Schrödinger system is a system of optimality condition for a concave maximization problem, which consists in maximizing a little term, which is the first guy minus this exponential term. So this is problem 12. And it is strictly concave in the sum, the direct sum of the phi I. So if I impose as a normalization, there can be only one minimizer, one maximizer. Okay, so existence I will discuss later, but uniqueness, as soon as I normalize, it can be taken for granted. Okay, so I will work basically in L infinity for the potential. I will look for bounded potentials which satisfies the normalization condition. So this is a space, Banach space, which I denote by E. And for a collection of potential phi 1 to phi n, where each phi I is in L infinity, I will define a map, a nonlinear map T. So T of phi is a collection T1 of phi, Tn of phi, where Ti of phi is in the corresponding L infinity space, which is just the average of this exponential. So Ti of phi at a point xi is given by the average with respect to all the other variables. It's a sort of convolution, if you want, of the kernel multiplied by the exponential of the other potentials, of the sum of the other potentials. Okay, so that is a smooth map. In fact, it's a C infinity. It's even real analytic. And the goal, given mu i's, I want to solve T of phi equals mu. Okay, so the range of T is obviously including in the interior of the positive cone, and in a subspace F, which is characterized by this compatibility condition we saw before, that the so F is a set of collection mu1 to mu n, which solves the compatibility condition that the integral of mu I and dmi should not depend on I. Okay. So with this definition, the Schrödinger system is just to solve the equation mu equals T of phi. Mu is given in this Banach space F. In fact, in the positive, in the interior of the positive cone of this space, and I look for potential phi in this space E. So here is the well-posedness results. So which says that for every mu in this F++, there is a unique solution, but the reverse map, which is a solution which I denote S of mu, as for Schrödinger, but this map is C infinity. Okay, so let me give the proof is very simple. It's basically based on the implicit function, on the local inverse, the inverse function theorem, plus some structural properties, and which and a computation I'm going to show you, and the Fredholm alternative theorem. We have to be a bit cautious because we are in infinite dimensions. It's a computation I want to show you. So. Okay, so let's start with local invertibility. So I have to invert somehow the derivative of this nonlinear map T. So it's convenient to take the log, the component-wise logarithm of this map, which I note T tilde. So T tilde, so it's a nonlinear map, and it has a very nice structure, a sort of diagonal part. So you see that T tilde I is just phi I plus an off-diagonal part, which is this logarithm here in equation 16. And I can differentiate. And when I differentiate the i's component, the T tilde I in a direction of some potential H1 up to Hn, I see that it is identity. This derivative has a nice structure. This is identity plus an integral. So it's a compact perturbation of identity. Okay, so when I differentiate this T tilde in the direction, I discover this Hi of xi plus this formula. But this formula is an integral, and being an integral, it has some nice compactness property, let's say in L2. Okay, and since so I want to prove that the derivative T prime of phi is invertible in some sense. So I will look for an H in the null space, and I observe that, of course, passing from T prime to T tilde prime is just multiplying by non-vanishing and bounded potential. So the null space of T tilde is the same as the null space of T. So I will work with T tilde and its derivative. So, of course, this expression for the derivative can be extended for an H which is not in L infinity, but simply in L2. If I do so, I observe that the derivative is a compact perturbation of the identity. So it's a good framework to apply the Fredholm theory. And to identify the null space, it's also convenient to introduce this probability measure on the product space, this Q phi. So now I'm the step of proving local invertibility. So phi is fixed. I'm gonna work in the neighborhood of phi. So here is this measure. It's a measure which is equivalent to the product measure M. And then it's convenient also for each I, it's convenient to disintegrate the measure Q phi with respect to its i's marginal. So I denote by Q phi I, the i's marginals, and Q phi -1 given xi is the corresponding conditional marginal. And now the off-diagonal part of the derivative of t, remember that I wrote it in a convenient way as identity plus L. The off-diagonal part, the L part, can be written as a sort of conditional expectation operator using this measure Q phi. So Li of H at the point xi is just the conditional expectation of the sum of the other potentials, the direct sum of the other potential with respect to the conditional probability Q phi minus y given xi. Okay, so it's a conditional expectation operator which is applied to the sum of the other potential, all the potential except I. So now let's take a direction in the null space. It means that Hi is the negative of this conditional expectation with respect to this measure, this conditional measure Q phi minus I. And now it's just an algebraic trick. Remember that I want to prove that I want to identify the null space of the derivative. So if I start from this relation, I take H in the null space, I multiply this guy by Hi of xi itself, and I integrate with respect to the ith marginal. So if I do that, I discovered that the integral of the square of Hi squared, the integral of the squared of Hi with respect to Q phi I is the negative of this sum of this sort of correlations. And now if I sum with respect to all the components I, there's a perfect squared which shows up. So I discovered that the integral of the sum, the direct sum of the Hi should be 0. In fact, it's H is in the null space of T prime of phi. Then it means that Q phi almost everywhere, the sum is 0. The direct sum is 0. Okay, it's just algebra if you want. But now it means that the null space, let's say in L2 of the differential, consists exactly of constants which sum to 0. So it has dimension n minus 1. But now if I normalize, remember that I was working in a space where I imposed some normalization, that the integral of the Hi dmi was 0 for the n minus 1 values of I. So the null space of T prime in this space is exactly 0. Okay. So the null space is dimension n minus 1. But now, because of the Fredholm theory, the codimension of the range is also n minus 1. But this is precisely the space, the dimension of the space F of compatible densities mu I, right? This is okay. So what have I proven? I've proven that in L2, I have some isomorphism. The derivative is some isomorphism between E and F, basically. But instead of working in L infinity, I work in L2. So, but in fact, all these operators and the inverse as well, if I have L infinity data, I send L infinity to L infinity. So this argument proves local invertibility. But I know also that globally, the nonlinear map T is 1-to-1. This is because the dual problem is strictly convex, is strictly concave. So there is uniqueness. And now there's also a topological trick that the range of the map, because of the local invertibility, I know that in F++ it is open, but you can also show quite easily that it is closed, and F++ is convex. So the map is also, the nonlinear map is also onto, okay? So in fact, I can pass from local inverse function theorem to sort of global version, which is quite classical, right? It is also ideas which goes back from Adama, I guess. And you can prove that the inverse is in fact a C infinity map. Okay, that's how it works. So it's a few lines of computation. It's just you see that it's nothing to do with the calculus of variations or whatever. It's just computing the derivative and computing a null space of a certain nonlinear map. Okay. How much time do I have? Probably 10 minutes or 5 minutes. Okay. Now let me mention. Sorry.
No, 10 minutes is fine. Perfect.
10 minutes is fine. Okay, I won't have time to go in the details, but now I will like to go. Okay, we're happy to know we can solve the system, and that the solution depends smoothly on the daytime UI. By the same argument, it also depends smoothly on the kernel. It depends smoothly if you add an epsilon far from zero, far from infinity. It's also the dependence is also smooth with respect to epsilon. This is just an implicit function theorem. But in practice, how do we solve the system? So it has been explained by Gabriel. We solve the system by a la Gauss-Seidel or by alternate maximization. We solve one equation at a time. This is a Sinkhorn algorithm. So again, same business. I want to solve the same system of equation. I solve them one by one. And the multi-marginal Sinkhorn algorithm it goes like this. By the way, it's the same as solving the Euler-Lagrange equation of a certain dual problem. Here, I've changed the sign, so this function f of phi is convex. I've multiplied the previous guy by -1. So it's a convex function. Okay, there's a linear guy, and then the integral of q phi, which depends in an exponential way on the direct sum of the phi I. And okay, I want to find a critical point of this problem 22. Of course, I impose normalization because otherwise I cannot guarantee uniqueness. So same normalization as before. I normalize the n-1 averages of the first potential of the n-1 first potential to be 0. So this is what my notation diamond means, zero mean, if you want. LP space with a diamond as an index will mean zero mean. And I'm considering the problem of minimizing this f of phi on the space on L infinity, but I impose the normalization of the n-1 potential. So now it's Sinkhorn. So it's a block minimization. So given phi t at the t step, I look at phi 1 t plus 1 by minimizing the function f with respect to the first marginal, where you have frozen the next components. So it is totally explicit. Okay, I don't want to get too much into this. There's a minus, there's a sort of log Laplace, and there's a normalization constraint, it's lambda 1t. And once I have the updated phi 1, I do the same for phi 2, phi 3, and so on. And I update the last one. There's no normalization because the last one is not unnormalized and gives this formula. I don't care too much about the formulas, but you see, this is exactly what Gabriel described. This is Sinkhorn in the multi-marginal setting. And my only assumption again is that C is in L infinity, so that K is in L infinity plus plus, the interior of the positive cone. The convergence of Sinkhorn without traits, using really heavily the fact that this is Gauss-Seidel, if you want, was observed in a very nice paper by Simone Di Marino and Augusto Girolin, but it came without weight. Again, as far as I know, that's why I was interested in this, the Hilbert metric proof and other proofs you can think of that do not work in the multi-marginal problem. That's why I was interested in this. And here is the result. It's a linear convergence result. Of course, the constant is extremely bad. It's exponential, is in the number of marginals, in the L infinity norm of the cost. If you put the epsilon, there's a 1 over epsilon in the exponential as well, as in the results Gabriel mentioned. But still, you got linear convergence, at least for the convergence of the energy in the dual problem. So you look at the energy along the Sinkhorn sequence, it decays exponentially fast with an explicit constant. And it is also true for the iterates. The iterates converge to the unique minimizer of the dual problem, which is normalized. In any LP, you can pass from, you can also do it in L infinity, but it requires other assumption on the cost. Okay, so how does it work? Just two words on the proof. The proof works like this. It's very standard, in fact, in optimization, at least in finite dimension, in convex programming. It's known that you have linear convergence of block descent, provided, let's say, in a Hilbert space or in finite dimension, you need two things. You need the energy to have a Lipschitz gradient and to have a Hessian which is bounded from below, which of course you don't have in the dual because you've got an exponential, so it's not true. But in fact, the Sinkhorn iterates, by construction, they are bounded, right? Because let me show you the iterates again. Let me show you the first one. So look at this equation 26. So you see that this phi1 has mean 0. And it's not difficult to see that whatever the other potential are, the L infinity norm, well, the oscillation of this guy is controlled by the oscillation of the cost. So K is exponential minus C, and the oscillation of K controls the oscillation of this sort of soft C transforms. So if you have zero mean and your oscillation is controlled by 2 times the L infinity norm of C, you are yourself bounded. So in fact, the phi t's are automatically bounded, something which was observed already by many people, including Augusto and Simone. So for free, you can notice that the phi t's, the Sinkhorn iterates, remain uniformly bounded, right? With bounds which are linear with respect to the bounds you have in the beginning in C. But now, what do? You're basically minimizing something linear plus an exponential. But okay, the exponential is bad on the whole space, but it's very good on intervals, right? And so, for instance, the detachment from its first order Taylor approximation is quadratic. So if you're on an interval minus m, it is true that the eigenvalues of the Hessian are bounded away from 0. And it is also true that the derivative is an exponential itself. It is true that the exponential is Lipschitz on every interval. Okay. So now from this, for a suitable constant, you see that the gain, the loss in energy on one step, full step of Sinkhorn from step t to step t plus 1 is controlled, is bounded from below by the squared L2 norm between the iterates themselves. Okay. This is strong convexity. Okay. So in particular, you see that the right-hand side in 3/8 is the term of a convergence series in L2. So in particular, phi t minus phi t plus 1 converges strongly in L2, and in fact in any LP. So from this, you can guess quite easily that there is strong convergence in an ALP to a phi bar which solves the Schrödinger system. You've got lots of compactness in the Schrödinger system, and from basically this super simple estimate 36, you can derive quite directly the linear convergence of the Sinkhorn iterates. Okay, and maybe it's a good time to stop and to, if you have questions, I'd be super happy to answer, right?
Thank you very much, Guillaume. Very nice talk. Has anyone questions? So if you're following online, you can just unmute yourself as usual, or someone in the audience, perhaps. Yeah, Gabriel, just a second.
Yes, just to clarify, so in the case of two marginals, your estimate are roughly matching those that you get with Hilbert divergence?
Absolutely.
So it's like exponential minus the infinite norm of the cost divided by epsilon.
Absolutely.
And it's more or less just a factor n that you have to pay when you.
Yeah.
Okay.
Exactly.
Super nice. Thanks a lot. And maybe it's obvious, but I guess.
Yeah. Maybe I should record. Sorry, Gabriel, to interrupt you. There are pros and cons in this result. Of course, it's crucial that the cost is bounded, which excludes interesting applications. So there's Gaussian kernel or the Coulomb cost and so on. But on the other hand, I'm in a quite abstract setting. The two results are in an abstract setting, right? These are abstract probability spaces. And what I require is that the cost is L infinity. So there's no topological assumption, if you want. It's just working in LP spaces.
Okay, and would this extend to things where the iterate would be less explicit, that if you, for instance, regularize with something else than the entropy, or I mean, instead of the Shannon entropy, you would be using another entropy function, for instance, or if we don't consider exact constraint on the marginal, but like unbalanced constraint or more exotic things that people would do in application?
It's a good question. I didn't think too much in detail, but probably on a case-by-case basis, it's probably to extend. It's probably possible to extend the results I showed to this setting. I agree. If you have some application in mind, I'd be happy, of course, to discuss it with you. Right?
About, I would say just simply what would be the hypothesis you need to put on the entropy function so that your reasoning would work, because it seems much more flexible than the Hilbert metric. So I guess this would be nice.
Well,
you do Dijkstra algorithm, but with something else than Kullback.
Well, you need basically locally strong convexity and Lipschitzianity of the gradient to the level of the dual function. You see, but locally. So other divergences are possible than Kullback-Leiber. I guess it describes a world class. It wouldn't work for a power, for instance.
Yeah, so I guess it wouldn't work for X square, right? Or would it? No, maybe it would.
But X square is special, right? But for X square, because it's exactly quadratic. But
well, what is popular in application is people that don't necessarily use Shannon entropy, but they could use X square entropy because it produces sparse less. It's a bit like having bounded diffusion support. So I think something that would be interesting in application. Okay, thanks, Guillaume. No.
Hello, Guillaume. It's Christian. Well, the cost is bounded, and you say it's crucial. But in some applications, if you make the hypothesis that the marginal are compactly supported, is it enough with to get the result and to go back to in some sense, since your cost is continuous and everything is interesting on a compact set?
Yeah, sure, of course.
Works, okay. So if you have a quadratic cost and compactly supported marginals, it's all right, okay?
Sure.
Okay.
But you see, I never said the word compact anywhere talking about the space. I didn't say anything about the topology of the space Xi.
Yes,
this is also a point I wanted to make. So what I need is bounded. So probably, I don't know. Now I have a question for you, right? Because I would have loved to be in Lisbon in front of you. I'd be interested also in application in infinite dimension, in the case where the Xis are in infinite dimensions. Because there might be cases where the cost is just bounded, but you make no assumption of continuity or nothing, right? Of course, if you have continuity, you see that you can use Ascoli, Arzeli theorem. Sinkhorn iterates remains in a set of uniformly continuous functions and so on and so forth, which I'm never using here. I'm just working in LP spaces. So yeah. To answer your question, yes, you can replace boundedness by. In your case, you are bounded because in fact you can work on the support if they are compact. It's fine.
All right. Thank you.
Thank you, Christian.
So since Max is away just for a few seconds, I actually have a question of my own, very much in the spirit of Christian's one is, so about your densities, your marginal densities, you assume that there's like strictly positive. So in the positive interior cone, so namely bounded, whose density is bounded away from below. Can you remove that? Because vacuum is important to allow for, right?
Okay, so this is for the well-posedness, okay? Where the MIs are whatever you want. But of course, if you want to have an analytic dependence with respect to the data.
Yeah, that's the smooth dependence, right? But as far as existence and uniqueness is concerned, this should not be.
I agree, but then
right?
it's not smooth. So just the result is false if you allow the mu i's to cancel, or it's really essential that all these measures, it's transparent in the proof. At some point I said that this measure Q5 sort of change of measure is equivalent to
right. So it's really the smoothness of the solution map, right? Not existence. Okay.
Absolutely.
All right.
Absolutely.
Yeah, makes sense. Yeah. Okay. Thank you very much. Anyone else maybe in the chat? I don't see any questions. Okay, so let's take a few minutes just to change slides, and let's thank Guillaume again.
Thank you.
Thank you.